Okay, let's talk about complex numbers. So before we do that, let's recall, right, that an imaginary number was simply just a number that when we square it, it becomes negative, right? So think about imaginary numbers like this. Like the purpose of an imaginary number is to make squares negative, right? So in our history, right, we or our math history, yours, we've understood that squares are always positive. Well, we need a number such that when we square it, it becomes a negative, and that's the purpose of an imaginary number. That when you square it, it's a negative, right? So imaginary numbers came from the need to solve this type of equation, right? X squared equals negative 1. A number, when we square it, is a negative. So we invented a whole new number system, right? We call them I. So when we square I, we get a negative number, right? And this is just like language. We needed another notation to represent the solution to this equation. So we just made up new words, all right? So we made up new notation. All right. So a complex number now is kind of the whole number system. So it turns out that imaginary numbers are only part of this new number system that we need, right? Or the new number system that was developed. Right? A complex number has the form a plus bi. So it turns out that a complex number is a combination of a real part, which is the a, and imaginary part, which is the b. Okay, the I lets me know that the imaginary part is the b. Okay, so make a note here. The imaginary part isn't bi. The imaginary part is the b, which these are both constants. A and b are just constants. And a and b will both be real numbers. They'll be the numbers that you realize, that you know, right? Twos, threes, negative sixes, that kind of stuff. All right. But the I lets me know that the number in front of that is the imaginary component. Okay. All right. So it turns out a complex number is a combination of a real number and an imaginary number. All right. So having said that, we can actually plot complex numbers just like we can plot real numbers like x's and y's, right? And we have the exact same coordinate system. We have an orthogonal coordinate system, and orthogonal just means perpendicular. And where we used to have the x-axis, now we have the real axis. So we'll plot all the real numbers on the horizontal, and we'll plot all the imaginary numbers on the vertical. Okay, so instead of x for the horizontal, y for the vertical, now it's the real is the horizontal and the imaginary is the vertical. Okay, all right, so let's try this. So here I have a complex number, 4 plus 5i. I want to identify the real part and the imaginary part of that complex number. Then I want to plot it. So 4 plus 5i. I have 4 real parts and I have 5 imaginary parts. And again, make a note. I didn't put 5i, right? Because I have 5 actual imaginary parts. The I lets me know that that's the imaginary part. The I is not part of the number there, right? Just lets me know that I have 5 imaginaries. All right, well, if I want to graph it, then I'll do my coordinate system. Instead of an x and a y, I'll put a real on the horizontal and an imaginary on the vertical. I'm going to plot it just like I would normal numbers. I have a 4 and a 5, so I'm going to do tick marks, 5 right, 5 left, 5 up, 5 down. And on the real, I'll go 4 tick marks over, that's a 4. On the imaginary, I'll go 5 up, so that's my 5. Again, I didn't put 5i, I put 5 because 5 is in the direction of the imaginary. So to graph 4 plus 5i, I just graph those pieces. I graph 4 and 5i. So this is the complex number 4 plus 5i. Okay? All right, there's a lot of similarities to our real numbers, right? Our x and our y. There's an orthogonal, right? Vertical and horizontal. We do tick marks like we always did. And we kind of treat the 4 as an x and the 5 as a y, right? That's how we think about it. All right, so stop the video. You want to complete classwork problem 1. Okay, for the next part, let's recall that I equals the square root of negative 1. And we actually got that because we did square root of I squared. And so I squared equals negative 1, right? So we really started with I squared, right? But we just took the square root of both sides. That's how we get I equals square root of negative 1. Okay, but just remember I squared equals negative 1. So now what I want to do is this. So let's simplify 2 complex numbers multiplied together. And how do I know these are complex numbers? Because there's a real part and an imaginary part. That's one complex number. A real part, and an imaginary part is just a minus. So I have negative imaginary parts, which is fine. So those are 2 complex numbers. Well, our distribution rules still apply. So it's just like we do, normal binomials multiply together. So I'll do, 1 times 2, then 1 times negative 3i, and then I times 2, and then I times negative 3i. Okay, so that's what I'll get with my distribution. So same distribution rules apply. And actually same operations, addition, subtraction, multiplication, division, they all apply. All right, okay. So now I'll just simplify. So 1 times 2 is 2, 1 times negative 3i is negative 3i, I times 2 is 2i. And notice what I'm saying here, it's subtle. The number comes first, then the imaginary part comes last. So here it's 2, and then 3, and then I. And then I don't put I2, I put 2I. All right, so the nomenclature is, or the standard is, we put the number first, then the I in the back. All right, okay, and then I have I times negative 3I. Just like variables, we only multiply like components together. So this is 1I times negative 3I. 1 times negative 3 is negative 3, and I times I is I squared. Okay, so it's just like you normally would multiply variables together. All right, so like variables, when we multiply them together, become squares. Okay, so now notice I have a negative 3i and a positive 2i. I have like terms, so I can combine those. And I have an I squared, which I know is negative 1. So I'm going to combine these two. So negative 3i plus 2i is just a negative I. And then I'm going to change I squared into negative 1. All right, and now I'm just left with negative 3 times negative 1. And then I combine like terms again. I have two real pieces, so 2 and 3 is 5. So 1 plus I times 2 minus 3i is the exact same thing as 5 minus I. That's its simplified complex number. Okay? All right, so stop the video and complete classwork problem number 6. All right, let's talk about complex conjugates. So we have a nice definition here. A complex conjugate are pretty much just two complex numbers with the same real part and opposite imaginary parts. Okay, and I'll make a note. Opposite in math means different signs. All right, so these are complex conjugates. I have 1 plus 3i and 1 minus 3i. They're complex conjugates because the real part of 1 is the same, and it's plus 3i minus 3i. All right, so when the imaginary part is opposite, when they change signs, that's a complex conjugate. And the real part has to be the same. So negative 4 plus I and negative 4 minus I, complex conjugates. Because the real part is the same, negative 4, and then the imaginary part changes sign. And even something like this, I and negative I, these are complex conjugates. It just turns out that the real part is 0. That's okay. We call this purely imaginary. All right, so when the I is the only part of the complex number, it's called purely imaginary. Likewise, if the real is the only part, then it's called just a purely real number. All right. Okay, so why don't you stop this and do classwork problem number 9. All right, our last piece is when we solve, solutions come in conjugate pairs. They're always come in pairs, and I want you to know why. All right, so let's solve x squared minus 6x plus 10 equals 0. There are no factors of positive 10 that will add to negative 6, so I can't factor this. All right, so I'm going to do quadratic formula. A is 1, B is negative 6, and C is 10. So if I put it in the quadratic formula, right, change in B squared. Oh, that should be a negative 6 squared. It'll still come out to be 36, but it should be a negative 6 squared. And then minus 4 times A times C all over 2 times A. All right. So if I do square the 36, or square the 6, I'll get 36 minus 40. That's a negative 4. All right, so I have 6 plus or minus, square root of negative 4 plus 2. And now if I take my negative 4, remember the square root of a negative is I. Square root of 4 is 2, so that's where I get the 2i. Okay, so I have 6 plus or minus 2i divided by 2. All right, so now I have a common denominator, so I'm just going to split them up. So I have 6 divided by 2 plus or minus 2i divided by 2. And now it's just simple arithmetic, right? 6 divided by 2 is 3. The 2's divide out, so I get an i. And so you see I'm left with x equals 3 plus or minus I. All right, and this comes out to be 3 plus I and 3 minus I. This is a complex conjugate, right? So these are conjugate pairs. So why is this a conjugate pair? Well, it's because of this plus or minus. And where did this plus or minus come from? Well, it came from the very beginning when I started with the quadratic formula, which was 6 plus or minus. And why did I get this? Because we started with a square. Okay, So why are complex conjugates, why do they always come in pairs? Because remember, we're always solving even roots or even powers. So the whole reason we came up with imaginary numbers is to find a number that when we square it, we'll get a negative. Well, when you square root when you square root a square, you have to include plus or minus. So you will always get this plus or minus because we're solving even powers. All right, that's why we have complex conjugates and their pairs. All right, it's actually the end of the video, so just stop this and do classwork problems 12 through 14.